In this video, we're going to learn 3 shortcuts for showing that two triangles are similar to each other. Just keep in mind that similar is not the same as congruent. They're the same shape, but they can be different sizes. The first shortcut is called AA, or angle-angle similarity, and it tells us really all we require are two congruent angle pairs. So if two angles of a triangle are congruent to two angles of another one, that's enough to say that the triangles are similar. So for example, if I take a look at these two triangles here, I've got one arc at A, another arc at E. So there's one angle pair that's congruent. We have double arcs at angles B and F. So that is enough to say that those two triangles are similar. So when we state that similarity statement, we need to be careful, just like when we stated the congruence statements back in chapter 4. We want to make sure that each angle vertex matches up with the corresponding, the correct one. So if we wanted to describe that, one way we could say that is triangle ACB is similar to triangle EDF. There are a bunch of other ways you could say that. That's just one example, but just be really careful that each angle vertex matches up with the corresponding angle vertex. The next shortcut is called side angle side similarity, and it's very much like our congruence for the side angle side with triangles. If you have two sides of a triangle proportional to two sides of another triangle, and the included angles are congruent, that's enough to say that the triangles are similar. So this is almost the same as side angle side congruence, with the exception that the sides don't have to be congruent, they just have to be proportional, meaning the ratios of their lengths are equal. So for example, here, if I take a look at those angles, A and E, they have arcs on there, so those are congruent. There's one angle pair congruent. And if I compare the sides, so when you're doing these comparisons, you always want to do small to small, big to big. So here I would want to compare AC to DE, because AC is the smaller side that I know of that triangle, and DE is the smaller side of the other one. If I compare 4 to 10, that reduces to 2 over 5. Now when I compare the bigger to the bigger, 8 over 20, that also reduces to 2 over 5. That means that AC and AB are proportional to DE and EF. This is enough to use side angle side similarity. So I can state triangle ACB similar to EDF. Now the included angle is really important. If we move where those arcs are, or where maybe even the segments are, the segment lengths, here I still have proportional lengths. 4 to 10 is still the same as 8 to 20. However, the angle pairs are not where they need to be. So ACB is not similar to EDF. We don't have enough to make that conclusion. So that arc would have to be where D is in order for us to be able to use side angle side similarity. The last shortcut is side 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 similarity. It's basically saying we don't need any angles as long as we know that all three sides are proportional to all three other sides. If we have that, then we can say that the triangles are similar. So for example, if I look at ACB and EDF, if I compare small to small, big to big, medium to medium, if I get the same ratio every single time, then those are going to be similar triangles. It doesn't matter which ones you compare to which ones, just make sure it's small to small, etc. But also make sure you do that in the same order. So if I was going to compare AC to, say, DF, because those are the smaller ones, comparatively speaking, I want to make sure that I still compare all of the parts of ACB to the parts of DEF. So let's see, 3 to 9, that's 1 over 3. 5 to 15 is 1 over 3, and 4 to 12 is 1 over 3. So small to small equals big to big equals medium to medium. That is enough to say that the triangles are similar. So those are the 3 shortcuts that we're going to use in this chapter for similarity.